In our next unit here, we're going to spend a significant amount of time bonding. Really, that's what this whole chapter is about, is bonding and the different types of bonding. Now, before we get too detailed on bonding, we want to remember why we are bonding. Going back to the periodic table here a little bit. Now, remember, elements are stable when their energy level is full. So when we get to this magic octet, so when we get to group 8 or group 0 electron configuration, that's when we have stable elements. So remember, knowing the numbers of valence electrons, I can't even write in order there. I got happy with another 8. 6, 5, 4, 3, 2, 1. Now remember, knowing the number of valence electrons in that outside energy level is going to be very important, because that is going to tell us how these things are most likely going to react and how close they are to achieving this octet. So again, if we're in group 7 and we're a halogen, we have 7 valence electrons, these things are likely going to gain 1 electron, form a -1 ion if they're forming ions. But they need 1 electron. These things need 2, tend to form -2. These tend to form -3. Again, carbon plus or -4. If it does that, these tend to lose 3, +3, +2, +1. Now, with that being said, there's not always a transfer of electrons going on in every chemical reaction or every chemical bond. Regardless, what we're going to have set up is a situation where elements, and particularly their nuclei, so the nuclei of different elements are going to attract the electrons from another individual atom. Okay? When we have this attraction between nuclei and outside electrons or valence electrons, remember this is only happening with the outside valence electrons. So we can call them outside electrons, or we can call them valence electrons. Or remember, they're the outermost S and P electrons. When there's an attractive force on those, it's from the nuclei of an opposite atom. So there's an atom attracting its electrons. When we have a pair of electrons that's being attracted by 2 different nuclei, that is called a chemical bond. That attraction is a chemical bond. And 1 pair of electrons being attracted constitutes 1 chemical bond. Or sometimes, well, let's just leave it at that right now. We'll get specific here as we go forward. So the first type of reaction we looked at just a little bit in the last chapter was we talked about a bond like this, where you have sodium, which, again, if we remember, so sodium, as we've seen before, is right here. It's in the first column, so it tends to lose 1 electron, especially if it's bonding to a halogen over here that has 7, and tends to gain 1 electron to get a noble gas electron configuration. So here, again, in this diagram, they're just showing their S and P electrons, their valence electrons. We notice the transfer. Again, when sodium loses that electron, it gains a +1 charge. Chlorine has its -1 charge, so they stick together. When that happens, when there's an actual transfer of electrons, it's called an ionic bond. So if we have an ionic bond, that is a transfer of electrons. However, sometimes we don't have a transfer of electrons because the things have very similar, what we'll call, or what we learned as far as their electronegativity. So if we look at sodium and chlorine, for example, their values here, chlorine is 3, sodium is 0.9. So if we look at those 3 and 0.9, they have an electronegativity difference of, about 2.1. That's a pretty high electronegativity difference, and we'll look at what's high and what's low here in a moment. But that's a high electronegativity difference. So that means one element's actually going to take the electron from the other. If we look at chlorine and chlorine, well, they're both chlorine, so they both have an electronegativity of 3. So they both have an equal pull on that electron. When that happens, we do not have an ionic bond because there's no electrons actually transferring. We have what's called a covalent bond. And that's when, instead of transferring that electron, what these 2 elements will do is they'll end up sharing 1 pair of electrons, and they will form, again, a shared pair of electrons, which is a covalent bond. So they have the 2 that are shared between them, and both of them still have their 1, 2, 3, 4, 5, 6 of their own, and the other chlorine has 1, 2, 3, 4, 5, 6 of their own. So if they have 7 each, right, and they share a pair, well, they'll keep 6 of their own. Then they'll have 2 as a shared pair, but that way they maintain or achieve an octet. And again, they bond that way because their electronegativity difference between 3 and 3 is 0. So not one can pull it from the other. They end up sharing that pair of electrons. So that's our difference, and the difference, again, is really based on the level of difference in their electronegativity. If we have a covalent bond, we have really close electronegativities. If we have an ionic bond, we have very divergent or very different electronegativities. If we look at these values typically just as something to look at, when we have covalent bonds, this tends to be between a nonmetal and a nonmetal, like chlorine and chlorine, or other examples we'll look at. If we have an ionic bond, this tends to be between a metal and another metal. I'm sorry, that's not true at all. Let me erase that. A metal and this would be our non-metal. So let's look at the electronegativity chart. So if we draw our zigzag line in here, if nonmetals here with high electronegativities bond to each other, we tend to see covalent bonds. But if we have something from over here, a nonmetal, bonding with something from over here, a metal, well, they have a different enough electronegativity that we tend to see more ionic bonds. Okay, so this is just a general observation that metals to nonmetals are going to form ionic bonds. Nonmetals to nonmetals are going to tend to form covalent bonds, again, because their electronegativities are very close, where the difference between metal and nonmetal electronegativities is a lot bigger. Let's just look at a couple other examples of covalent bonds. Hydrogen bonding to hydrogen is probably our perfectly covalent bond, where each has one proton, one electron, to fill its s orbital. And now, hydrogen and helium are two elements that actually do not want to form an octet because they're just not big enough. They form what's called a duet, which means two electrons in their outside orbit because all they have is an s orbital. So that makes sense. But if we look at hydrogen here, it's still going to form a covalent bond. So covalent, again, hydrogen has an electronegativity value of 2.1, as does any other hydrogen atom. So when they come together, they have equal poles on each other's electron cloud. And so this blue is supposed to represent, again, the probability graph of where that electron is. It's electron cloud. Notice when they come close to each other, the opposite nuclei attracts the other one's electrons until they merge their electron clouds and share a pair of electrons, like this indicates. Now, a lot of times how we will draw these is as Lewis dot structures, where we'll draw the element with its number of valence electrons, element, number of valence electrons, and then to show the bond, we'll connect those. Notice in an element, so hydrogen, again, a covalent bond, sharing that electrons. Oxygen, again, has very high electronegativity, as does another oxygen atom. When it bonds, though, notice oxygen has 6 valence electrons. And again, I'll write this as what's called a Lewis dot structure, because sometimes we can see that better. So it has 6. And notice if it shares one pair, well, then each one has 1, 2, 3, 4, 5 of its own, and then a pair sharing it would be 7. So what needs to happen for oxygen is oxygen needs to share 2 pairs of electrons. So each one has 1, 2, 3, 4 of its own. This one has 1, 2, 3, 4 of its own. But then these two and these two are going to be shared in the bond, and we draw lines between them to connect them. That is showing a double bond, and that is okay. We can share 2 pairs of electrons. So notice again, though, we still have 8. We have 2 electrons here, 2 here. That's 4, plus the 4 that are shared for 8. 2 here and 2 here, plus the 4 that are shared for 8. Notice we can make, obviously, covalent bonds between atoms and other types of atoms. It doesn't only have to be to itself. However, when it's not bonded to itself, then we have to introduce some new terms. So what we've been talking about so far is nonpolar covalent bonding. That's when we have 2 elements of either equal or very similar electronegativity bonding together, where their overall electronegativity difference is 0 or very close to it. We have something called nonpolar covalent bonding. Now, if we have 2 nonmetals bond together, and they have a difference in electronegativity that's significant, and we'll define what significant is here in a moment, then we have something called polar covalent bonding, or we have what's called a polar bond. So again, chlorine bonding to chlorine would be an example of a nonpolar bond because they're equal electronegativities. However, if we have hydrogen bonding to chlorine, now hydrogen, like it says, has an electronegativity of 2.1. Chlorine has electronegativity of 3. So if I draw chlorine, again, chlorine's in the 7th column, so it has 7 valence electrons. It has an electron here. It has a stronger pull on that electron than hydrogen. So when this bond forms between these, notice the electronegativity difference here, and I'm just writing it in absolute value terms, is 0.9. Now 0.9 is not strong enough to rip that electron away from hydrogen, but it's strong enough to set up what's called a polar bond, or a polar covalent bond. And what that means is that this electron from hydrogen is being pulled more towards the chlorine. So there's unequal sharing. So sometimes polar bonds are called unequal sharing. It's still sharing. The chlorine has not ripped the electron away like an ionic bond, but it's not sharing very equally. It is like that big sister you had when you were 12 and you got an Atari for Christmas, and you're supposed to share it between you and your sister, and then your sister didn't really share it with you very much, and you wanted to play pole position in Donkey Kong. You couldn't really do that because it wasn't being shared. Actually, they didn't have Donkey Kong on the Atari 2100. They did have pole position, though, and Qbert they had, and some other games. Centipede. Oh, that's Centipede. Anyway, so we have a polar bond being set up, an unequal sharing of those electrons. We can also have it, obviously, with other elements that have a difference in electronegativity. Here's an example of the electron cloud between hydrogen and fluorine. Hydrogen's a very electronegative element, hydrogen slightly less so, and so we have that electron cloud being distorted and pulled more towards fluorine. And like this shows, what these symbols mean is it means, well, when that happens, we get a partial negative on our fluorine. Not a full negative, but that symbol means partial, and a partial positive charge on our hydrogen. So these are what we consider our cutoffs. So a covalent bond, and again, we should think of this as more of a spectrum than as hard, fast cutoffs. So from 0 to about 0.4, we think of as a covalent or a non-polar covalent bond, because their electronegativities are so close, or are virtually close enough that it really is insignificant difference. There's not really a shift of the electron cloud. However, above 0.4 all the way to about 2, we consider polar covalent, because now we have enough of electronegativity difference that electron cloud is shifted towards the more electronegative element, building up a polar bond. And a polar bond is just like, it's a pole, just like a mini magnet. There's a positive side and a negative side. So we have a positive side of a molecule now, and we have a negative side. And like you can probably guess, it's going to act like a little magnet, where positive will stick to a negative, and negative will stick to a positive. But we'll talk about that more later. Right now, we just want to figure out what they are. So we have a non-polar, when it's below 0.4, between 0.4 and 2.0 is a polar covalent bond. Above 2.0, we consider it an ionic bond. Now, that electron has been ripped away. We have a positive ion, we have a negative ion, and they stick together. So it is a spectrum. So sometimes things that are right on the line, sometimes we'll call them polar covalent, sometimes they'll be ionic. It really depends on like the size of the element, its electronegativity, what type of compound is forming, how many other elements is bonding to. So there's not a fast, hard cutoff, but that is the cutoff that we generally use. So here's it in another form. So between 0 and 0.4, we consider nonpolar covalent. From 0.4 to 0.2 is polar covalent, and above 2 is an ionic bond. Now, some things we want to talk about when we have these ionic bonds. So we've looked at an example like this, where again, chlorine has an electronegativity of 3.0. Sodium is about 1.9, so the difference is at 2.1. So again, over that mark, not huge over that 2.0 mark, but it is over that mark, so we can actually have a transfer of electrons. One thing we want to think about when we think about ionic compounds, which is different than our covalent, remember, it's between a metal and a non-metal. That's one way we can identify an ionic bond. Other ways, before we talk about other ways, let's look at some other examples. So we don't have to have a one-to-one transfer either. Notice chlorine has 7 valence electrons. This chlorine has 7 valence electrons. So when it tries to bond to calcium, if we go back to our periodic table, calcium is right here. It is in group 2. It has 2 valence electrons. So again, if it forms a bond, especially an ionic bond, it is very likely to lose 2 electrons. And again, metals, if they're not bonding to themselves, they are forming ionic bonds primarily. So calcium has 2 to lose. Each chlorine wants 1, so that means it has to bond with 2 chlorine. It can't just bond to 1 chlorine, because 1 chlorine cannot hold 9 electrons in its octet, because an octet is 8, and 8 is the maximum number of electrons it can hold in its outside energy level. So when calcium is bonding to this chlorine, it needs to bond to 2 chlorines. So it transfers 1 electron to one electron to the other, since it lost 2 electrons, it gains a +2. Each chlorine has a -1. And that little 2 there doesn't mean a -2 charge. It means there's 2 chlorines. So the way I would rather write it is say chlorine has lost 2, so it has a +2. Chlorine has a -1. But again, when they bond together, we need 2 of these. So how we write it is CaCl2 would be the formula for our compound. Notice anytime our metal, calcium, bonds to a non-metal with 7, it's going to bond to 2 of them. It's going to lose 2 electrons. Here's an example of calcium bonding to fluorine. Calcium becomes a +2. Each fluorine is -1. We would write that formula as CaF2. Now notice here's a more crazy example. Aluminum, which is a metal again, when it bonds to oxygen, which is a non-metal, aluminum has those 3 valence electrons because it's in the 3rd group. If it wants to bond to oxygen, well, it can't just bond to one oxygen, because if it loses 2, it still has 1 more to lose, so it has to bond to another oxygen, but then that oxygen's not happy, so it has to bond to another aluminum, but then that aluminum has 2 left, so it needs to bond to another oxygen. So what we see is that for these things to bond, there needs to be 2 aluminums and 3 oxygens for everything to maintain and achieve a noble gas electron configuration. Last piece we really want to say about these ionic bonds as well is ionic bonds are very different than covalent bonds. Again, when we have a metal bond with a non-metal, not only do we get a transfer of electrons, and we get this electrostatic attraction between a positive and a negative ion, a cation, remember, and an anion, but also we form an ionic lattice. We form a repeating structure of positives and negatives. So the interesting thing about our covalent is most of our covalent compounds are what we call simple covalent compounds. So if we have oxygen and it's written like this, well, that's all there is there is O2, and that's all there is. But when we write, say, NaCl, there's not just one Na and one Cl. It's actually a repeating pattern of NaCls. And so it's a lattice, and this is just what we call the smallest repeating unit of the structure. Now, because of these ionic structures, what we see for ionic compounds, now most covalent compounds like this tend to be gases, or they tend to be liquids, whereas our ionic compounds tend to be solids, and they tend to have very high melting points. So high melting points because it takes a lot of energy to break apart that whole lattice structure, so they have high melting points. They tend to be really strong compounds. This is probably a better chart to summarize these concepts than trying to read my writing there. So ionic, like we said, happens between a metal and a metal, or more often between a metal and a non-metal is probably the more proper way to write it. So there's a transfer of electrons where, again, as opposed to our covalent, there was sharing of electrons. And again, these happen between non-metal bonds. Again, our ionic compounds, because of their lattice structure, they have high melting and boiling points. Covalent compounds tend to have lower melting points and lower boiling points. That results in covalent compounds tending to be, not that they can't be solids, but they tend to be liquids and gases at room temperature, where ionic, almost as a rule, are solids. Well, as a rule, I can't think of any exceptions. They are solids at room temperature. Ionic tend to be hard and brittle, have very strong bonds. Now, it says covalent are weak bonds, but they're weak in relation to our ionic bonds. They are weaker than our ionic bonds, maybe we should say. Ionic compounds also are electrically reactive, which means they will conduct electricity in certain conditions. If they're liquids or if they're dissolved in water, they do conduct electricity. Covalent compounds tend not to conduct electricity. Ionic compounds, almost, again, as a rule, not all of them, but almost as a rule, they dissolve in water, like sodium chloride. Most covalent compounds do not. And also on ionic, this might be getting a little off of what we need to know, but electron orbitals are separate, which means there's actually a transfer of electrons from one to the other. In our covalent, they are overlapping and sharing their electrons, so their clouds are actually overlapped. So far we have covalent bonds, which again are a full sharing of electrons that have really close electronegativity, slightly higher difference in electronegativities, again 0.4 or higher on our scale. It gives us polar covalent bonds where we have an unequal sharing, so we have a pole or a positive and negative side of that compound building up. If we have, again, above 2.0 in electronegativities, then we have ionic bonds where that electron actually gets taken away. They form strong lattice structures. They have all of these traits of really strong bonds. They're solids. They have high melting boiling points. And also, If we have metals just bonded to metals, then we have metallic bonds, and those properties we're going to look at later, but they bond completely different. So metals we'll set aside by the side right now, and we'll just look at bondings between elements that are either covalent or ionic.